So I want to thank everyone for their time today. I know for some of us we're headed into the second day of the conference, so I appreciate the time to present. So I'm going to leverage the very nice introduction that Daniela has already provided to really sort of just dive right into the presentation. It's a little bit different title than was presented in the agenda because I really wanted to take a step back from showing you just examples of distributed analytics to sort of how we're developing that for a specific node, the National VA transform. And so really this work comes out of the pScanner Analytics Work Group, which Daniela, Michael Hogarth, and myself lead. And the objective of this group is to really perform the analytics that the pScanner CDRN need to execute in its 3 use cases. And so the technical framework that Daniela showed you earlier is really the focus of this talk, particularly as you transition from all of the standards into a specific node implementation. And so one example of this, as she mentioned, was the Oceans and GLORE analytics. And so as an Oceans as an example, what you would do is you would take in the PMML and other data standards. At the node level, you would then translate those data standards into node-specific code. In the case of Oceans, you would basically translate QMF into Microsoft SQL or into Oracle SQL or into whatever your installation is, and then do an in-database execution to transform your common data model, whether that's I2B2 or OMOP, into a flat analytic file that then you could conduct your analysis on. So for the Oceans adapter, it would basically take in a PMML input, translate that internally, take the flat file input that was translated from HQMF, and then execute the analysis request on that, and then basically wrap the payload of that back out to a data standard and translate that back out to the coordinating node. So these are just some of the analytic techniques that Oceans supports. Really, most of these we intend on being replaced by the R infrastructure that we're building. And I think some of these sequential analytic techniques, which I'll conclude the talk with, are really the pieces that we'll be using to do our distributed analytics. So in the R case, we're planning on developing an infrastructure that allows the massively parallel R instances, R and Oracle and Revolution Analytics R, to basically take in, translate a query, convert the whole query from the source data model to the flat file generation, to the analytics request, and then to the resulting output through into an R module, execute that internally at the node in whatever instance that the node chooses to set up, and then wrap that again in data standard representation and package that out to the data center. And so we're for the VA, we're going to be building first a pilot in just using an RServe instance that's a Linux multi-workspace instance, and then we want to extend to is a Revolution Analytics R in Hadoop installation, which is going to allow a lot faster processing of the data. But we want to be able to support other nodes in pScanner to be able to do much smaller installations, either single-threaded or single-server installations, as well as there's some interest from one of the sites to do an R and Oracle installation, and so we're going to try to support that as well. I believe Michael Hogarth is going to be evaluating the capacity for our translation engines to support that node implementation. So really the purpose of this is to really allow a broad range of analytics capacity at the node level, from relatively serial single requests at the time to potentially 5 and 10 concurrent analytics requests at the same time. Initially we're going to be using RODBC connectors to basically pass the analytics request in through R, and then R directly connects to the database at the node to again reduce transit time and processing time, bringing the computation to the data. As is an emerging theme for the talk. And then one of the best parts about R is there's a lot of support already in place in R modules to do the conversion out to the PMML modeling standard for the predictive modeling outputs. And so next, so one of the interesting things that Daniela mentioned earlier, and I agree with her, is that there's going to end up being a tree structure where you have a central pScanner coordinating node, and then it's going to send out a distributed request to each of the individual sites, the UC sites as well as the VA site. Well, then within the node itself, you'll actually have another central cluster which will basically bring in analytics requests to that center, and then to either parse out the analytics request to multiple statistical engines so that you can load balance your analytics requests so that you can scale your capacity for concurrent analytics requests. And so this is an example. I won't go into detail, but it's a representation of R in Oracle, where you essentially have your an R enterprise installation within the Oracle database. You have an R client, so you can basically send in your analytics requests into the database, but which gets actually on server processed, so you aren't doing large-scale data transfers out to the client. And that's one of the ways that you can implement parallel processing. Another example, as she mentioned, was R in Hadoop, where basically you have an R client that connects directly to a Hadoop instance and then uses specialized packages to execute the map and reduce functions and analytic functions necessary. So I'm going to transition from more of the nodal implementation to some examples of distributed analytics that we've been doing. So one of a lot of the work that we do is comparative effectiveness, whether it's medical device comparisons or medication exposure comparisons between A versus B. And when you're doing that work, in observational cohort data, you have to basically adjust for confounding and do an account for those. And so one of the ways in which we do that is using a propensity score match proportional difference sequential analytic technique, where you design your comparators, you build a propensity score on the exposure, you match your groups between exposed and unexposed, and then you analyze the proportional differences between the two groups. So the benefits of this really are that you can generate your matched cases and controls, you can adjust for confounding among your variables for the variables that you're including in your propensity score model, and you can use a large number of covariates in the model because it's not subject to the same overfitting that a predictive analytic model would be. And also for the proportional differences, you can analyze different sample sizes between the groups. It's interpretable if one of the groups doesn't have any events, and you can implement in a serial cumulative fashion. So to give you an example of that, I won't go into the actual study details, but this is a representation where in the background you have a logistic regression model that was generated to predict the outcome of interest. You apply that to your data set. You basically compare the observed rate and your exposure of interest in comparison to the expected outcome rate generated by your risk prediction model, and then you basically serially compare those, and the confidence intervals indicate the certainty around which you've done your estimation. If your lower confidence interval exceeds the line, you have a sustained event rate, and if it doesn't, you don't. I think one of the implications for this type of analysis in multi-node privacy-preserving analytics are that you can use something like GLOR to basically generate a global risk model across the sites, bring that into each of the sites, execute the risk model on each of the sites, get your aggregate counts of outcomes and denominator exposed, then you basically take those aggregated numbers, bring them up to the coordinating center, and you can do your analytics, truly aggregating all of the site's data in the analytic framework without exposing case-level data. So this is a method that works very well for that sort of distributed analytics. This is another example of a representation of the same sorts of risk-adjusted SPC, where instead of looking at it in a proportional difference perspective, you're just looking at it in an event rate where you have an observed event rate of an exposure of interest. You're basically comparing your expectation based on a propensity score matched comparator group. So it's a prospective concurrent control where you're matching exposed device versus a comparator device, looking at your event rates, and if your observed event rate for your medical device exceeds the expectations from the baseline device, you have an alert or you have an alarm. One of the limitations I think that Fern was mentioning is when you're doing a propensity score matching, you can still build your underlying propensity score using something like GLOR, where it's a global analytic risk model, but you still have to bring down the match into your individual sites because without the ability to see the case level data, it becomes more difficult to basically match a case from one site across to a case from another, depending on how you're stratifying your analysis. So there is, I think, some work still to be done in basically doing cross-site matching. There's also some statistical considerations and concerns when you're doing cross-site matching because there's unmeasured confounding that you can partially account for if you're doing within-site matching that you can't necessarily if you're doing cross-site matching. So there's multiple statistical considerations that you need to deal with when you're doing that in a distributed analytics framework. Another example of a sequential analytic method is sequential probability ratio testing, where you again use logistic regression, survival analysis, a predictive analytic technique to form your expectation for your analysis. And then you plot the observed cumulative log likelihood ratio for a given institution, provider, site of interest, and you're basically looking for a deflection outside of your event range. So the good utility of this type of method is that if you're looking across a distributed network at 100 different sites, like in the VA, I think there's 138 different independent electronic health record instantiations. And I know that changes, so that number is probably off by a slight number. You can actually do a distributed analysis request where you're doing a risk-adjusted surveillance for acute kidney injury or for mortality, looking at the high and low performing centers. So you could imagine distributing this across a wider network, looking across multiple healthcare systems. And this sorts of analytic methods can be used to do that type of work. So lastly, graphing and visualization. So some of the work that we've been doing with Lucilla and Fred Resnick and others within the P-scanner and scanner work, as well as some of the NLM work that was done prior to that, is doing visualization and graphing of these methods. So we have web-based components, Java-based components that can basically be plugged into a framework to be able to visualize your propensity score matching and your sequential analytic methods so that you can display those in a portal. And just in conclusion, we're developing multiple interfaces for different nodal implementations so that we can take the standardized representations of the analytics and implement them at an individual node. I think that's going to be an ongoing effort where as a node comes online and really says, well, I need SAS and Oracle, I need Microsoft SQL and R, I need Stata, we'll have to sort of develop additional adapters for some of those instances as we need to do that. Hopefully over time we can develop a library of interfaces that handle most of those cases. And I'm happy to take any questions.
All right. As I said before, it's an honor to be working with these smart people on all these techniques. So any questions from the audience? Let me ask the panel to start coming, and I'll ask a question during that time. So my question is, to what extent this could also be used for examination of genomic data from the Million Veteran Project, for example? How different would that be?
Yeah, so that's a good question. So the question is how applicable are these types of methods for incorporating genomic data? I think the challenge in that is representing the genomic data into more of a flat file analytics where you have features, genetic features that you basically merge in with the phenomic features, and then once you do that in a representation for whatever level unit of analysis that you're interested in, then you can basically directly apply the same sorts of methods using that. But I think that the step from source genetic data to roll-up representation, that's sending a lot of work under the carpet. But I mean, the methods potentially could be applicable after you clean and transform the data sufficiently.
Yeah, so as you see, it was a guiding question because I trust that that's exactly right. The million genomes could be used in a distributed fashion to provide results combined with other data sets. So I think just because they're at the VA, it doesn't mean that they won't be usable by others. Of course, there are many details to be done. So I'd like to thank Michael. He will be here for a few more hours.